Okay. So what I tried to do here, and I don't know if this works, you'll have to give me a comment on it, but what I tried to do here was show two situations. And what I probably need to do is put some lines in this table where I'm sort of showing one situation on the left, talking about what it happens, and then what happens if we change it. So what we see is that under most normal circumstances, that magnetic field that's in the nucleus affects nothing. Okay. Because all of the nuclei can basically just, their magnetic fields can be pointing in all different directions. And again, one of the problems that we have when we talk about chemical systems is that we talk about, one thing sort of representing the system, but really chemical systems are all collections of a large number of similar objects, right? So, we talk about here's an atom, but really, if we were to ever really work with it, we would have, a mole of these atoms, right? And so what I tried to do here was sort of imply that, we have a whole bunch of nuclei. The nuclei are all the same. They're all hydrogens, for example, but they're together in a collection. We put them together and then we look at how they're behaving. Their magnetic fields, if they're not in an external magnetic field, if they're just by themselves like most objects normally are, their magnetic fields are pointing in every direction. We go to this one, it points that way. Go to a different one, it would point in a different direction. Okay. And there's, in theory, basically almost infinite directions if you get down to, so many sig figs, and it's just totally disordered. And therefore, we don't really see any net effect of this. Any effect that would happen would cancel out. They all have the same amount of potential energy. It's not really useful to us. But if we put a magnetic field on these things, so basically what that means is if we take a magnet and we put that sample, which has all those nuclei in it, in the center of a magnet, then the big magnet, this one here that we've put it into, and all these tiny little magnets will interact in the same way that if we bring two bar magnets, the north will repel, the south will attract. And basically what happens is the little spins line up parallel to the external magnet, but the external magnet is pointing in a direction. So if we bring in our other little spin, it could either go in the same direction, that's parallel, or it could be pushed to flip in the other direction. And that probably just is a matter of like a spin that's almost pointing up. If I put the magnet in, boom, it pops up. Whereas a spin that's almost pointing down, boom, if I put the magnet in, it pops down, right? You could kind of imagine how that would work. And so what we do is we create what we call two spin states that are very well defined. And one of them we call the alpha spin state, and the other one we call the beta. And basically the alpha is the spin state where it's pointing in the same direction as the magnetic field. And the beta is the spin state where it's pointing in the opposite direction of the magnetic field. And so that's represented here. In theory, this over on the right-hand side is the same set of nuclei as we started with before the magnetic field. And you can see that we're going to use these big arrows like this to represent magnetic fields. And the typical symbol that's used for putting magnetic fields into equations in physics is the letter B. And so we say this is B, the magnetic field, and the ext means external. It's not inside the molecule, we're putting it from the outside. So when B external equals 0, they all look like this. When the magnetic field is not 0, in other words, it exists, they line up. Now the significance of this then, I'm going to show you, is this picture, which shows you essentially we're talking about the similar system. And I forgot to put my little circles here. So let me just show you. So we had all those magnetic fields pointing in various directions. And I don't know if I got all the directions or whatever, right? So when there was no magnetic field, we had all those nuclei. Each nucleus points in a different direction, but they're all at the same potential energy. Then when we impose the external magnetic field, which I haven't drawn here, okay, but it would be that big arrow, then we see these nuclei split up, and some go into the alpha state and some go into the beta state. So it's really the same thing I showed you above, but we see that the beta state has a higher potential energy than the alpha state, because in a sense, the beta state is fighting against this large external field, and it's using effort to do that, right? It's doing work. And so that means it has a higher potential energy. Okay. And so now I have 3 nuclei with a lower potential energy, 3 nuclei with a higher potential energy. And what we also have then is a potential energy difference, a delta E between these two states. And that is what makes NMR useful, because once we have a system that has a potential energy difference, then we can put energy in from the outside and cause things that are lower energy to move to a higher energy. Okay. Now, so we're going to be very concerned about the size of that potential energy difference, right? We have nuclei that look like this, nuclei that in the alpha state, we have nuclei in the beta state. And what we're going to talk about is the net magnetic field. So we put a magnetic field on there, and then there's going to be things that are going to add to it and subtract to it. But whatever, the total magnetic field that nucleus feels at the end, okay, is called the net magnetic field. And when that magnetic field is 0, as I just showed you, all of the nuclei have the same potential energy, and therefore our delta E is 0. But it turns out as that field is applied and gets bigger, as the size of that magnetic field gets bigger, the two states, the potential energy splits apart. And the bigger the field, the farther they are apart. And it's the distance apart between these two states that is delta E. Okay? So the take home then is that the bigger the magnetic field, the bigger the difference in energy. Okay? Now, I'm going to need a little bit of an equation to kind of show you how this all works out later. But there is actually an equation for calculating exactly how big is that energy difference. And it uses, it looks like this. The energy difference is equal to this. This is actually the letter gamma, okay? And it's a constant, and it's different for every isotope, okay? Times Planck's constant divided by 2 pi, okay? And so basically this entire portion right here is actually a constant. Okay. And then we have our net magnetic field. So basically what we're saying is delta E is equal to a constant multiplied by the net magnetic field. In other words, they're directly proportional, right? Just a perfect linear relationship there. So you don't need to worry about this. I don't expect you to do math with this. Some of the textbooks, they introduce this and then you do some of the calculations. I don't really see the point in that, because that's not what, you only do that if you're building an NMR or something like that. And you're not going to build an NMR, you're just going to use the data. So, but I just want you to be aware of this, because we're going to use this later to prove the relationship between the magnetic field and a frequency, okay? So again, the important thing is to note that we have a delta E between these two states, and we have a relationship delta E times a constant equals the magnetic field, or the magnetic field times a constant equals the delta E.